Okay, in this example, we have an airport considering 3 different display panels for their air traffic controllers. The airport simulated an emergency, and 4 controllers were randomly assigned to each type of display panel. They recorded the time in seconds it took each controller to stabilize the emergency condition, conduct a hypothesis test to determine if the type of display panel affects the true mean time to stabilize the emergency condition, and find and interpret R-squared. So first of all, when we look at this, we notice that there's 3 different types of panels. There's the A, B, and C. If I look at my little chart here, it seems like A and B aren't necessarily too far off from each other, but C seems like it's quite a bit higher than the other, so C is probably pretty slow. We probably wouldn't like C. Let's see. We also have our nice chart here, okay, with all the outputs, so we don't have to do it by hand. So you can see for each group, there's a sample size of 4. You can see each of the sample means and sample standard deviations. And then we have our ANOVA table. Okay, remember when they say treatment, that means which group they're in. So the treatment is which group they're in. And from here, we can do all of our hypothesis tests, and all the work is, well, all the numerical work has been done for us. You just have to know all of the statistical things. Like, one of the first things we have to do when we do a test is we still choose alpha. You have to be able to write the null and alternative hypotheses. The null hypothesis is always that the means are equal. So like the mean of A is equal to the mean of B is equal to the mean of C. And the alternative for ANOVA is always going to be something like at least one population mean is different from the others. And then we keep just pulling stuff off of here. So we always look for a test statistic. In this case, it's really easy because you just come here and you find F on there. The test statistic is 30.11. There you go. Okay, then you find the p-value by just looking at the chart. It's 0.0001. Well, comparing that to alpha, 0.001 is much smaller than 0.05, so this is a small p-value. And we reject the null. Now that was a pretty small p-value. We rejected the null, so we can say that we have extremely strong evidence that at least one of the population, let's see, population mean, we'll call it response times, is different from the others. Now remember, this one doesn't actually tell us which one is bigger, or maybe they're all different, maybe 2 are the same and 1 is different. It doesn't really tell us that. If we want to know which one is different, well, you can use your intuition and guess which one is probably different. I guess the C is probably different, but you'd actually go on further and do a post hoc test and a pairwise comparison to see which mean is really different from the others. And then finally, we were supposed to find R squared. R squared is defined as the sum of squares for the group over sum of squares for the total. So for that, we just come up here and look at our chart. So sum of squares for the group is that treatment SS, so 500.17, and sum of squares for the total is 574.92. This gives 0.87. And what does that mean? This means then that we can explain, let's see, 0.87, so 87% of the total variation in response times by which group the controller is in, or which group, or basically type of display panel the controller was in. And that's really high. That means that we can really explain a lot of the differences between the times based just on which group they're in. And that means the group is having a big effect. In our next example, we just want to practice pulling all the values from the table, because this is something that I would ask you to do on the exam. And here's the display panel table, ANOVA table from up above. I just copied it down here so we can see it. Let's see, so as we go through, I might ask something like, tell me the group mean square. So remember that treatment is always your group. So mean square, if you really don't even remember anything about it, but you had to guess which one is mean square, I would guess the mean square would be the MS. So 250.83. Now total sum of squares, SS is sum of squares, look at the total row, looks like we're at 574.92. Let's see, total degrees of freedom, so degrees of freedom, total 11. Sum of squares for the error, so SS, error, 74.75. Mean square for the error would be MS on the error row, so 8.306. Okay, group sum of squares, that would be the group or treatment row, so the 500.17. Let's see, error, degrees of freedom, is 9. Our F-test statistic is here at 30.11, and our p-value is 0.0001.